Our direct comparison test tells us that if we have some series of b sub n and it's convergent, and we have some other a sub n that is smaller than or equal to b sub n for all n, well then the series of a sub n is also going to be convergent. And similarly, but vice versa, if we have some series of b sub n that is divergent, some known divergent series, and we know of some other, or we have some other a sub n that is greater or equal to b sub n for all n, then the series of a sub n is also going to be divergent. And this makes sense because if we have some a sub n that's smaller than a convergent series, well, you know that this converges to some finite value, so the one that's smaller than it must also converge to some finite value. And if we have some series of b sub n that just goes off to infinity, it's divergent, and we have some series that's greater than that, for all n. Every a sub n is greater than every b sub n for all n. Well, this thing is also going to shoot off to infinity. It's also going to be divergent. So your direct comparison test is sometimes called DCT for short. This is good for p series and geometric series, or series that can be somehow algebraically manipulated so that they can look like a p series or a geometric series. And we're going to look at one that right off, it may not be obvious that you could treat it similarly to a p series, but let's just take a look at it and see what happens. Here we have the series from 1 to infinity of -1 to the n times n factorial, all of that over n plus 10 factorial. Okay, now this is not a p series necessarily, because we have these factorials here, because we have the -1 to the nth power. So in essence here, this is an alternating series, and we want to find out maybe if it is absolutely convergent or what have you. So if you try some other tests, initially, for example, you might be thinking, oh, well, it has some factorials in here. Let's just try the ratio test and see if we can get rid of these factorials. But what you get if you try the ratio test, let's see, this is what would we get if we tried the ratio test. That would be the limit as n approaches infinity of the absolute value of, now here we would have a -1 to the n plus 1 power. Remember, whatever's on the numerator is going to be, all the n's are going to be added plus 1, have 1 added to them. -1 to the n plus 1 power times n plus 1 factorial. Well, that's just going to be n plus 1 multiplied by everything less than that, so in other words n factorial again. And we can do this as a ratio in the numerator. Sometimes people like to go ahead and write this as a fraction, and then what would be in the denominator, flip it and multiply it towards the inverse fraction. But I like to keep each expression as it were, and just put a sideways fraction here. Here we have n plus 1 plus 10 is going to give us n plus 11 factorial. N plus 11 factorial is just going to be n plus 11 times everything beneath it, n plus 10 factorial again. So then we're going to have a denominator that's just going to be this. So we have negative 1 to the nth power n factorial, all of that over n plus 10 factorial. Well, right off the bat, we see that our n plus 10s here and our denominators, those are going to cancel out. Our n factorial terms, those are going to cancel out. And these negative 1 to the n plus 1 or negative 1 to the n, these aren't going to matter because we're taking the absolute value here. So we can go ahead and just ignore these. And what we are left with, this is just goes to the limit as n approaches infinity of n plus 1 over n plus 11. And as n goes further and further to infinity, this 1 and this 11 become increasingly insignificant, and what this goes to is just n over n, which is 1. Well, we know just by the definition of our ratio test that if the limit as n approaches infinity of all of this goes to 1, then our test would be inconclusive. And if the ratio test is inconclusive, then we also know that the root test would be inconclusive as well. So here we have no conclusion. No conclusion. And it's important, even though you might have had a hunch that this would work or not work, just to go ahead and try it. And if you hit a brick wall, at least you know that it's a process of elimination, and you've ruled out this possibility. And we can take a look at some other ways of evaluating this here. Now, I know because we have this negative 1 to the nth power times n factorial here, well, this is just going to be negative 1 to the nth power times some b sub n, and our b sub n is going to be this positive part here, this n factorial over n plus 10 factorial. So what we can do is we can test for absolute convergence. We can test for absolute convergence. So I'll go ahead and rewrite it here. N equals 1 to infinity. Negative 1 to the n times n factorial over n plus 10 factorial. This is just equal to the series from n equals 1 to infinity of negative 1 to the n times b sub n, where b sub n, like we said, is all of this stuff here. So if we test for if we test the absolute value of this, we're just going to get b sub n. So let's go ahead and do that here. We have the absolute value of negative 1 to the n. That's just going to get us to b sub n. And b sub n is just equal to n factorial over n plus 10 factorial. Now notice, as our b sub n goes to infinity here, as our limit n approaches infinity of b sub n, well, this is just going to equal n factorial over n plus 10 times n plus 9 times n plus 8 times on and on and on times n plus 1 times n factorial. And our n factorials here are going to cancel out. You're just going to have a 1 up here. And I want you to notice that actually we didn't really need to take the limit as n approaches infinity. I just did that to illustrate what would happen, if n just went on and on and on here. Notice that this is going to be smaller. This is going to be smaller than this is going to be smaller. So b sub n is going to be smaller than the series, or than the sum a sub n that we can build a series on of n to the 10th power. Because this n factorial here just cancels out with this n factorial here. What we're left with is just 1 up here. And then we have 10 terms down here. We're going to have 10 terms of n plus something multiplied by one another. So what this is going to be is some polynomial that's going to start with n to the 10th power plus, n to the whatever else power, on and on, and plus a constant. And because this denominator here is going up, then the whole fraction is going down in value. So this b sub n is going to be less than if we just had 1 over n to the 10th power. So when we build a series on this, we can see that if we have a series of some b sub n, which is what we had up here, and another series here of some a sub n, well, we know that this converges. So this is n equals 1 to infinity, n equals 1 to infinity. Doesn't have to start at 1, could start at whatever else, but here we started it at 1. Because this series converges, this is just a known convergent p-series. And because it is greater in value than this series that we built on b sub n, and it just goes to some, converges to some finite value, and this is less than that, so this is just going to converge to some lesser finite value, well then this is also convergent. So right up here we could write that our series, this converges absolutely by the direct comparison test. And we're not evaluating this to figure out what it equals. We might need to use a computer algebra system or something like that to get the answer for that. But we just care about whether or not it converges or diverges, and we have shown that absolutely it does converge to some value.